Some animals bite. Some sting. Some inject venom. This one does something far more dangerous. It explodes from within, again and again. Logic says it should die with the first shot. Instead, it can set off that explosion hundreds of times over a lifetime. Picture this. A frog swallows the beetle whole. The hunt is over. Or so it seems. 2 seconds later, the frog's mouth snaps open, its head thrashing, and the beetle walks out alive. It didn't escape before being swallowed. It made its own predator spit it out. The strangest part isn't that it can trigger a chemical explosion. It's that the explosion happens inside its own body, and it survives to do it again. Turn over any stone in a temperate forest anywhere in the world, and you'll likely find one. A dark, almost metallic body, under 2 centimeters long, thin legs, antennae that never stop moving, reading the air before the eyes confirm anything. Motionless in the damp soil, it looks exactly like what it is, one more insect among thousands. It's called the Bombardier beetle. Not for how it looks, but for what it does the moment something gets too close. It fires, with an audible crack, like a tiny pocket cannon. There are more than 500 species scattered across the world, all grouped under that name for one obvious reason. They all share the same impossible system inside. No claws, no jaws capable of piercing skin, no venom in its legs, no stinger. And it isn't especially fast. A wolf spider the same size catches it in under a second. A shrew can cover 30 times its own body length in that same instant. A bird spots it from the air without any effort at all. Within that group, it belongs to the species science has studied most, the ones living under leaf, litter, stones, and fallen branches, in the same corners where toads, shrews, army ants, and dozens of insect-eating birds go looking for a meal. On paper, it's the perfect prey. The right size for a bird. The right texture for a toad. Most insects in that position solve the problem by hiding. They blend into a twig, a dry leaf, a patch of bark. Others rely on warning colors. Red, yellow, orange, a visual signal that touching them comes with consequences. This beetle does neither. Its color is unremarkable. Its shape mimics nothing. It doesn't need to hide because it doesn't depend on going unnoticed. It depends on what it carries inside. A toad camped beside the same stone already avoids it entirely. Its behavior around this particular beetle is nothing like how it treats any other insect its size. A column of army ants moves across the leaf litter, dozens at once, ready to tear apart anything in their path. The beetle doesn't run. It stops. It lifts its abdomen slightly toward the front and fires. The first ants in line recoil instantly. They freeze for a moment, as if deciding whether to push forward or pull back entirely. The ones behind them change course without ever making contact, veering off to the sides. None of them try again. Within seconds, the whole column flows around it, like a rock splitting a river, and moves on without it. The beetle stays exactly where it was, still, as if nothing had happened. None of this comes from its legs, or its shell, or any burst of speed. It comes from its abdomen. Inside, it holds 2 substances that, kept apart, are reasonably stable. Most animals with chemical defenses store them already mixed, ready to release at any moment. This beetle does something different, and far more dangerous. It keeps the ingredients separate, only millimeters apart, inside its own body. And it decides, in the exact instant it needs to, when to combine them. What makes this insect remarkable isn't that it can produce an irritating substance. Plenty of beetles do that, with secretions that simply taste bad or smell worse. What makes it unique is that this substance is born from an explosive reaction, generated on demand, inside a body that should be destroyed in the process. And it isn't. Remember the frog from the beginning. The beetle disappears inside its mouth. For any other insect that size, the hunt would end right there. Inside the beetle's abdomen, something switches on. Two chambers, separated by a valve, begin draining into a third. One holds hydroquinones, the other, hydrogen peroxide. It has carried both its whole life without any trouble at all. Stable until they touch. Inside that final chamber, the two substances meet a set of enzymes acting as a catalyst. Steam rises, the same way it rises from a kettle at a boil, except there's no flame underneath. There's a chemical reaction happening inside a living body the size of a fingernail, inside a predator's mouth. The frog has no idea yet, but it just swallowed something close to boiling, the exact point where water stops being a liquid. 2 seconds. That's all it takes for the frog to react. What follows is pure survival instinct. It shakes its head violently, rubs its face against the ground, against a rock, against anything within reach. Tries one thing, then another, desperate to get rid of whatever it just bit down on. Until it works. The beetle drops to the ground. Covered in saliva, it walks a few steps and disappears into the grass. The frog never tries again. The pressure from that reaction forces the liquid through a narrow channel. Toward a nozzle, the beetle can aim with precision at almost any angle of attack. The result is a hot jet, forceful enough to produce an audible crack. A researcher holds one of these beetles with tweezers and presses gently on one leg. The shot lands directly on the fingers, a sting of heat. Hours later, a dark mark still lingers on the skin. And that's the effect on a hand tens of thousands of times larger than the beetle itself. No tissue inside the beetle shows any damage after the shot, no internal burns. No visible trace of the explosion that just occurred millimeters from its own organs. The first hypothesis was simple. Maybe the beetle can only fire once. Maybe that hot burst empties its chemical reserve completely, leaving it defenseless for the rest of its life, weapon spent. Field data contradicts that from the start. The same individual fires at the same attacker. Then at a different one, seconds later. Then a third, not long after that. Whatever happens inside that abdomen isn't one explosion. It's many, one after another, too fast for the frog or the human ear to ever tell apart. Now we know what the frog felt. A camera built to capture thousands of frames per second is trained on the beetle's abdomen at the exact moment it fires. At normal speed, everyone sees what the frog saw, a jet, a crack, nothing more. In slow motion, that image falls apart completely. The shot isn't one. It's dozens, one after another, at a rate no ear could ever separate. Slows to 500 micro-explosions per second, bundled into bursts of roughly 70 consecutive shots. All of it within a fraction of a second. 70 shots. In the time it took the frog to start shaking its head. No one in that original scene ever knew it. Neither the frog nor the beetle seem aware that something closer to a machine gun burst just took place. The first researchers who studied this with a stopwatch and an ordinary camera had no way to detect that fragmentation. It took technology capable of freezing time, frame by frame, to see what's really happening in there. Think of a piston inside an engine. Up, compress, fire, down, and up again. Over and over, without the cylinder ever breaking apart. Something similar runs inside the beetle's abdomen, a valve opening and closing in a constant cycle, letting just enough liquid through before cutting it off. The same way a pressure cooker's valve releases steam only when pressure rises and seals shut the moment it drops. 70 times in the time it takes an eyelid to blink once. That fresh liquid entering with each cycle serves a second purpose. It cools the chamber walls before the accumulated heat can damage the enzymes that make the whole reaction possible. The fuel itself cools its own engine. No sound betrays that machinery at work. Only the final crack. Only the jet. The rest of the process happens in silence, hidden inside a body the size of a fingernail. There's more. The nozzle isn't fixed in place. In some species, it can rotate nearly 300 degrees on its own axis, enough to aim forward, sideways, or straight back, without the beetle ever needing to move its body. That precision matters most when the attack doesn't come from a mouth, but from something that grips. An ant that manages to pin the beetle by one leg has no way of knowing the abdomen can swing toward it and fire directly at the exact point where it's holding on. It lets go instantly. 70 micro-explosions, aimed with precision in any direction, shutting themselves off before any damage is done. But the frog never saw what had just happened inside that abdomen. In an engineering lab in the United Kingdom, a group of researchers watches a mechanical replica of the beetle's reaction chamber. No one speaks. All eyes are on the same spot, a cylinder barely 2 centimeters long, wired to a system of electrically heated water. No hydroquinones, no hydrogen peroxide, just water. The goal isn't to build a weapon. It's to understand and copy something far more valuable. The valve system that lets you generate repeated explosions without destroying the container that holds them. For months, this team works on something that sounds almost absurd from the outside, trying to make water explode in a controlled way, over and over, inside a tube the size of a finger. The jet fires across the lab and hits the far wall, more than 4 meters away, in pulses. Following the same principle of filling, ignition, and release that operates inside the beetle's abdomen. Someone points at the watermark on the wall. No one says anything for a few seconds. They've spent months chasing exactly this result. The engineers gave the technology a name. They called it micromisting. On paper, a fire extinguisher and a 2-centimeter beetle have nothing in common. One is built in an industrial plant, out of steel, its pressure regulated by mechanical valves. The other fits in the palm of a hand and builds itself inside a living body. But the principle that makes both of them work is identical. Release a substance under pressure, in short, repeated pulses, without the system collapsing under its own heat or force. It's the same problem facing a car engine. The same one facing a fire extinguisher. The same one facing a medical inhaler, which has to release an exact dose of medication as a fine mist, again and again, without ever failing. A fuel engineer spends years calculating how to inject fuel into an engine in millimeter pulses, at the right temperature, at the right instant, without letting the accumulated heat damage the system. A 2-centimeter beetle solved it millions of years ago. No blueprints, no calculations, no engineer behind it. The beetle didn't design its valve system from nothing. It inherited it, generation after generation, from much simpler chemical defenses found in other beetles, ones that release only an unpleasant secretion, no explosion, no heat. The extreme version we see today is the result of millions of small adjustments, each one slightly better than the last, accumulated over a span of time no human engineering team could ever afford. Nobody designed this weapon with the end result in mind. Nobody planned the valve system, or the rotating nozzle, or the exact balance between heat and protection. And yet, there it is, working inside the abdomen of an insect that fits on the tip of a finger. Go back to the scene from the beginning. The frog, its mouth snapping open. The beetle walking away, covered in saliva, toward the grass. It's easy to assume the extraordinary part is the explosion. The heat, close to boiling. The audible crack. Chemistry capable of dropping a predator in under a second. But any unstable substance can explode. That takes no engineering at all, just the wrong ingredients, together, at the wrong moment. What makes this beetle remarkable is exactly the opposite. It's the ability to trigger that explosion hundreds of times, inside microscopic chambers, centimeters from its own organs, and keep walking afterward as if nothing happened. It's a valve system opening and closing 500 times a second. It's the fresh liquid entering each cycle, cooling what the last one just heated. It's a nozzle that rotates nearly 300 degrees to aim exactly where it's needed. Any violent chemistry can destroy. Very few systems in nature know when to stop. A wildfire also releases heat and pressure without control, and it builds nothing. It only consumes. The difference between that fire and what happens inside this beetle's abdomen is the same difference that separates an explosion from an engine. One destroys everything it touches. The other turns that same violent energy into movement, into defense, into life that continues. That's the real evolutionary achievement hidden inside a 2-centimeter insect that most people never even notice when they turn over a stone. It didn't invent fire. It learned to shut it off before that fire turned against it. Millions of years before the first combustion engine existed, before any engineer ever sketched an intake valve, this mechanism was already running, generation after generation, inside a body that fits on a fingertip. No one designed it. No one calculated it. And yet it solved, with absolute precision, one of the hardest problems there is: how to hold power without being destroyed by it. The frog is still on that same bank, long after it's all over, its mouth closed now, its eyes fixed on the grass where the beetle disappeared. It never knew it had just witnessed a perfect engine, and that same stone beneath your feet in any forest on Earth might be hiding exactly the same secret. The closer you look, the stranger the world becomes.